We try to build robots that learn a little bit like humans do, by trial and error. What we've done is train an algorithm to solve the Rubik's Cube one-handed with a robotic hand, which is actually pretty hard even for a human to do. We don't tell it how the hand needs to move the cube in order to get there. The particular friction that's on the fingers, how easy it is to turn the faces on the cube, what the gravity, what the weight of the cube is, all of these things, it needs to learn by itself. The interesting thing is that kind of standard techniques in robotics haven't been able to scale to that complexity that we see in a robotic hand. Humans have evolved to be able to manipulate and operate our hands. So there's a huge amount of learning that's happened through evolution to get us to this point as a species. And the robot has to learn all of this from scratch. Instead of trying to write very dedicated algorithms to operate such a hand, we took a different approach where we create thousands of different simulated environments and learn to do the task in all of those, and hopefully the robotic hand will be able to do it in the real world as well. This means like thousands of years of experience that this neural network has had in simulation. Every time the algorithm has gotten good at the task, we make the task harder. That's really crucial because it needs exposure to really complicated environments in order to eventually be robust to the real world. You put a rubber glove on the hand and can still carry out the task. This ability to generalize to new environments feels like a very core piece of intelligence. It really changes the way we think about training general purpose robots. Moving from thinking too much about the actual algorithms and start thinking about how do we create complex enough worlds where they can learn. At some point, then it would be more down to the imagination what robots could actually accomplish. The hope is to build robots that can do many different tasks, to increase the standard of living and give everybody a better life.
All right. So a demonstration how reinforcement learning can be applied in the real world. And here's like actually solving the Rubik's Cube. And so you can see it's robust to different kinds of obstacles and manipulations. Like they put a rubber glove on the hand and it still performs well. I can skip forward. They tie two fingers together and it still works. They cover it with a blanket for some time and it can still figure out after. They put random objects in front of the camera so to obscure the view. It's random other stuff too. Yeah. So it's pretty cool what we've developed with just reinforcement learning from trial and error. So that's reinforcement learning. So now we'll just go into the slides here. So basically reinforcement learning is a process of learning from trial and error, and it uses a reward and punishment system. So the reward can tell the agent how well it's doing over time, and you can see like in the bottom you have this Mario game. And as Mario gets near certain like enemies, you can see that the reward graph over time here dips down because it expects that it might die and get a very negative reward. So can see other examples of reinforcement learning, and we can use it in self-driving vehicles and in many games. Tend to do that a lot because games are good ways to model the real world, maybe a very crude way, but at least we can perform simulations without actually having to interact with a very expensive environment. So say you won't have to buy the hardware for a whole robot and then practice in the real world. But it can still be applied to the real world. It's just that you would have to have many interactions with the world, and sometimes those interactions could be very devastating. Like if a self-driving car does one action wrong, it could kill a person. And so we generally tend to train things in simulation before we deploy them in the real world. So let's start off with the basics. So we start with a reward that just tells agent how well it's doing. So it's a scalar feedback signal. It indicates how well agent is doing at time step t, and its job is to maximize the cumulative reward. So the cumulative reward is just all the reward over time, and so by maximizing that future reward, then you can achieve the highest possible reward, and that means that is the agent's goal. So that's what the reward hypothesis is saying, is that all goals can be described by the maximization of expected cumulative reward. So say over the lifetime of a person's life, if their goal is to be happy, then to achieve their goal, they would try to maximize their happiness at every time step of their life, for example. And so sequential decision making is the process of making decisions over time. And so our goal, as we mentioned earlier, is to select actions that maximize total future reward. And there's can be multiple dynamics in this this decision process. We could have actions that have long-term consequences, and rewards might be delayed until the future. And then it might be better to sacrifice immediate reward to gain more long-term reward, or vice versa. So say you have an exam, but you want to play some video games. A long-term reward would be doing well on the exam, and then that impacting your future. Short-term reward would just be playing video games to relieve stress. And then return. So the return is basically a sum of rewards over time, but these rewards are weighted over time as well. So as you can see here, gt equals rt plus 1 plus t plus 2, etc. And then we have this gamma term. This gamma term is between 0 and 1, usually around 0.9 or 0.99. And so as you go farther in time, the term is exponentiated higher, and so we have the weight decreasing over time. So we would have something that's closer and closer to 0 as you increase the amount of time steps, because the reason why is so that you don't keep waiting forever until you finally get your reward. You want to actually balance in some intermediary between achieving immediate reward and waiting to achieve a higher reward in the future. All right. So next is the agent and environment loop. So the agent acts in an environment. This can be a robot or a game agent in a game. But the agent itself, you can think of it as just a brain, because it would basically be the program that runs the robot, for example. And then, so when the program decides, given an observation through its sensors and then a reward through some mechanism, it can decide what its action is to do and say it's moved this joint by 45 degrees. And then, so that action gets inputted into the environment, and the environment then determines what happens next. So if there was a water bottle here and I knocked it over, then that is what the environment decided to do, and so it gives you the next observation. The observation would be the water bottle falling over or something. So, and then also gives you that reward, and it would probably be a negative reward because it was not very desirable. And then you increment the next time step, and then so that loop goes up around and around. Okay, so now we have our history and state. So our history is basically everything that we saw previously. So our observations, our rewards, and our actions for everything from the beginning up to the current time step. And then our state is just some kind of information that summarizes the history, and that is used to determine what happens next. So it can be a function of history, and is basically a summary of all the previous states also. So how does that play into reinforcement learning? Well, now we have this thing called an agent state and an environment state. So the agent state is all the information the agent knows, and it's the information that it uses to predict the next action. And so it could be an interpretation of sensor data or any perception data. And using that, and also, as we mentioned earlier, the agent state is a function of its history. Okay. So also we have the environment state. That's what the internal state of the environment, and this could be a lot of information. So it's all in the information of the environment. It's usually not visible to the agent, of course, because if you're just in a room, you can't see what's outside of the room. And it may contain irrelevant information for the agent, say if the robot never leaves the room. And so that is denoted as SE versus SA. But this environment state is typically not used and not approximated. So now we'll go into more definitions of the state. So there's something called an information state or Markov state. This is basically a state that contains all the useful information from the history and uses it to predict what will happen next. So say in this equation down here, basically the first term is saying the probability of the next state given the current state, and that's equal to the probability of the next state given all of the previous states. And that is also equal to the probability of the next state given the history. So you can see that the relation of the history is equal to all of the previous states. And because of our Markov assumption, we only need to have the immediate state before, which ST, to predict the next state, ST plus 1. So it's just a summary of everything, right? So that's the term, this sentence in B also, it's another way to frame it. And so because we have this assumption, we can just do an iterative loop instead of having to know everything in the past at each iteration. So there's two different kinds of environments. There's fully observable environments and partially observable environments. So fully observable environments are where the agent observes the whole environment state. So say you are in a board game and the agent is playing chess. Because the agent sees the whole board, it knows the state of the board, and therefore it can predict the future on what moves to play next. Say if it's partially observable, that's more like a real world environment where you have an agent in the more real-world environment where it's limited by its perceptions. Say the sensor has a limited amount of data it can handle, and instead of giving a state to the agent, you give the observation to the agent. And its observation is usually the subset of information of the whole environment. And so this is called a partially observable Markov decision process, or POMDP. And then the fully observable environment is called MDP. And so these two things, MDP and POMDP, is basically a term to label these environment loops. And for a lot of problems, if you formalize that as MDP or POMDP, you can use any RL algorithm to solve your problem. So, oh, and the last thing I wanted to mention here is if you have a partially observable environment, remember that our agent state is a function of the history. So we also call that the agent's belief state, because it creates this belief that it's in this current state, and so it can produce actions. But it may not necessarily be in that belief state. It might be in an actually different state because it's not given enough information in its observation. So maybe a robot doesn't see enough in its environment, and so maybe it's actually in a different position than what it believes to be. Okay, so there's three major reinforcement learning components. There's the policy, value function, and model. So our policy basically says what strategy should you use to choose actions. And so it's also the agent's behavior function. So given a current state, what action do I select, right? And then our value function, it asks the question of how good is this state or action. So it's the agent's prediction of future reward. And then our model is basically how does one state transition to the next state. And then this is the agent's representation of the environment. So if the agent has some theory of what the probability distribution of going from one state to another is, then that would be the agent's model. So all three of them may not necessarily be inside of an RL algorithm, but they can be very useful components. And the policy is always necessary, however. So let's go on to our policy. It's basically our behavior. So our policy inputs a state, basically, and outputs a function, or it's a function that outputs an action. And so we could have either a deterministic policy or a stochastic policy. So a stochastic policy would instead just sample from a probability distribution one action. Say if you have a normal distribution, you can say our action would be sampled from there, and you pick some point. And then now we move on to our value function. So our value function predicts the future reward from a given state. And when I mean future reward, we go back to our expected reward or return that we've talked about earlier. So this is basically the expected sum of the future discounted rewards and then given some state we're in. So you can see here we have RT plus 1 plus RT plus 2 times these gamma terms, and they increase over time. So this just predicts the expected reward you'll get. And then we can also have our different function that computes the same thing, but with additional information when we select an action. So if we select an action as well, you can compute a function that computes the expected reward for that action in combination with the state. So say you have a deterministic function and you can choose to go left or right. You can have a state action value function that predicts what's the reward for going left and what's the reward for going right. Okay, so and then our last thing is their model. So our model predicts what the environment will do next. So right here we have our two models. This is the regular state model and then state transition model, and this is the reward model. So, and it predicts basically what the reward function in our environment would do. So in the environment, it has its own state transition model and reward model, because otherwise this agent would not get any information about its states. So these are inside of the environment, but we can also put them in the agent if we want to. And so basically this notation here just says given state equals S and action equals A, what is the probability of the next state st plus 1? And then for the reward function, we say given, oh, that's an error right there, so that shouldn't be, it should be R, but anyways, given the previous S and A, what is our, what is the next reward? Okay, and so when we put this all together, we can just construct a small diagram here, and the orange thing is the agent and the blue thing is the environment. And so we start off with our agent, say it has some state and it produces an action. The action goes to our environment, and now given its current state and action, it produces the next state. So the next state goes back into the history of the agent for logging, and then we can also produce a reward for the next state, so SA, and then we get RT plus 1, and that can be logged for the agent, and then the agent will do some kind of learning from the history, so now it knows what happened in the past, and so it can try to update its values and its policy. So also for partially observable environments, now we are not given the state directly, so you can see there's no arrow going directly to the state here. Instead, we're given observations and rewards, and they are appended to the history, but now the history goes through a function to produce the belief state for the agent. So now we have this bigger loop where now the history is fed through a function to produce ST, and this function could be anything from like a RNN, a recurrent neural network, or convolutional neural network. Typically RNNs are used now. So yeah, and then we still have the state function here in the environment, but it's not shown to the agent, and instead we have an observation function that produces observations to the agent. So here's basic formulation of the in the RL loop, but there was some more stuff here, but I deleted it for the sake of time. But basically, I mentioned briefly the Markov decision process, and basically we just need some kind of state transition dynamic that also is conditioned on actions. So we have actions in the loop, and so all that is saying is that that a given state is independent of any previous state transitions. So the probability of transitioning into a given state is independent of any previous state transitions. So you have that Markov assumption we mentioned earlier. And so like in a board game, for example, you know what to move next, because you don't have anything that's time dependent, right? You know everything in this state. Okay, so here's like a small overview of the kinds of algorithms there are, because like in academia there's like thousands of research papers and algorithms you could try, but here are the most notable ones. I think these ones might be already out of date, but this was the most recent graph I could find. So there's policy gradient. So usually you can divide RL algorithms into model-free RL and model-based RL. Model-free is when you don't have the agent learn a state transition model. Model-based is when you do. And then in model-free, we have policy optimization and Q-learning. Policy optimization, you directly optimize the policy based on data, and Q-learning, instead you learn a value function from your data. And then you can have things that also learn both, and we call these actor-critic. And there's a bunch of algorithms here, but so far I'll just give a brief overview of policy optimization and Q-learning. So Q-learning in a nutshell, basically, so what this graph is showing is we have our state space like in 3 dimensions. So the x and y dimensions are just like maybe xy coordinates. And so we're trying to find the future reward. And it turns out that at point S3, we have the highest future reward. And so what Q-learning does is essentially, for any given state, it just records what direction would have, or it records the direction of reward. So for any given state, basically it would say this, pick this action because that would maximize your reward for any given state. Okay. Any questions on this so far? Okay. So, and now we go on to policy optimization. And for this one, instead of having a state space, we have a parameter space. So we can have a policy like a neural network that has different parameters, and by adjusting different parameters, you can end up in different regions that have high reward versus worse reward. So if you have a bad policy, you would want to try to incrementally update it to the better policy, and you can do that by maximizing this performance function, or essentially minimizing the negative performance function or minimizing the loss function. And that you can do with gradient ascent, because now instead of descending, we want to ascend to find the highest possible reward. So to summarize the difference between Q-learning and policy optimization and why they're used in different circumstances, Q-learning essentially learns the value function and indirectly learns the policy. Sometimes it's more sample efficient but hard to get working without tricks. And actually recently, the second claim is not true even. I think policy optimization now works better. So I think for going in the future, usually just go with policy optimization. So in policy optimization, you directly learn the policy, but it's sometimes more robust, but it also needs more samples. But maybe that might be not true, because there's so much research going on that like these claims become false all the time. And so I'm personally doing research in deep RL, and so I read a lot of papers and like a lot of things change. So combining the two, you can have actor-critic, learns the policy and value functions, and a lot of works tend to go with actor-critic because you can use the most information available. Okay, so we'll just go quickly over policy optimization, and then we'll go over some of actual code. Okay, so we assume that we have some data set of experience. So, and this T here is a trajectory. And what a trajectory is basically a collection of states, actions, and rewards at each time step. So we can expand this trajectory over T time steps with observations, actions, rewards, or states. And so we want to pick actions given the states so that we accomplish some goal. So say our policy is A given S and our parameters. And so we have a probability distribution of picking A given the previous things. And so we want to maximize our performance function, and this defines how well our policy is doing by saying, let's just measure it by the expected reward for a trajectory. So we have this trajectory sampled from our policy, and then we just take the expectation of the reward of that policy. So to find this out, basically you would just run your agent in an environment for a bunch of time steps, and then just like average that reward, and then that number would be your value for your performance function. Okay. So, and it's similar to a cost function because instead we maximize the score instead of minimizing it. So to learn a better policy, we just want to figure out how to change the parameters of J in such a way that it increases the performance function. And to do that, we do gradient ascent. So basically, we can turn our performance function into a gradient, and then by incrementally finding the slope and finding the derivative, we can try to incrementally go up the gradient to find the global maximum. And then we have our update function basically here. So update our parameters by a small amount according to the gradient of the policy. And this is called the policy gradient. And so this was again the formula. Is that clear, or should I go again on this? I think we're good, right? So to calculate this gradient, because our current performance function is just expectation over T, we don't have anything in terms of our data, which is our states, actions, and rewards. So how do we derive that is the question. So how do we get from this thing, this gradient, to something that contains our variables of S, A, and R? So to do that, we say first, what's the gradient of our expected reward? And so through probability rules, we can change the order of these. So the expectation first goes into an integral, because now we have, if we take the summation of the probability of trajectory happening times its reward, and we take the integral of that, we essentially get the same thing as the expected reward. So this is according to probability rules. And then for the next part, going from this, the gradient of the integral of this, we can switch it according to calculus rules. And then going from in here, basically we take the probability of a trajectory and multiply it by itself over itself, So now, basically, we just took a probability of a trajectory divided by a probability of a trajectory, and if you divide it out, it equals to 1, so we can introduce this term. And according to calculus rules on this thing right here, the gradient of something over itself is equivalent to the gradient of a log of that thing. So if the derivative of log of x equals a derivative of x over x. So, and lastly, we want to change this thing back into our expectation, because this is the same thing as undoing what we did in the first step. So I turn the integral of probabilities back into expectation form. And then we have this thing. So in the purple thing right here, you want to turn this into actually using our policy. So this is the end term right here. So our goal is to get to that end term. And as you can see, we have our policy in there, but we don't have it previously. So to do that, we basically have to expand the probability of a trajectory. And so a probability of a single trajectory is a probability of being in some initial state times the probability of being the next state times the probability of choosing the action for that given state. And so we multiply this out, and using the probability chain rule, we can find the probability of the whole trajectory. And so when we take the log of that whole trajectory, we can basically turn the product into a summation, because that's what happens when you take the log. And now all the products become logs, or sum of logs. And so when you now take the gradient of that, because the gradient of this log right here does not contain any of the parameters of the policy, this is basically a constant, so it's 0. And the same thing goes with this term, because there's no parameters right here. This is essentially a constant, so the gradient of that is 0. And then we're left with this term here. So now we have that purple thing is equal to the sum over time steps of the gradient of the log of the policy. Okay. So finally, we just take the probability of trajectory and replace it for gradient log prob of policy. And so that is our final term here. And so to estimate it in practice, now we just have to average that term over our data set. So we calculate our estimation of the gradient. So for all trajectories in our data set, we basically average over them, and we sum from 0 to t of this quantity. Okay, and then instead of using like this term up here, the gradient of the performance function, we can use our estimated gradient g, and then update our parameters. Okay, and then so that's how you get this term here basically, and that is all you need to. That's like 90% of the work to implement a policy gradient algorithm. But of course there's like other stuff here, but I'll just show you that in code. So that's what we're going to do next. So we have our policy gradient implementation. I just posted that on a new repository because we didn't have one for the spring 2020 workshops. So here is our code in Collaboratory. So basically we import the standard libraries like OpenAI Gym. It's a great resource that has a large collection of environments you can train on and test on. And then we're using PyTorch here. So we create our environment first. I guess I could start running this to see how it goes. Okay, so we're gonna train in our cartpole environment. And basically if we Google OpenAI Gem, we can go to our cartpole environment here. And as you can see, it's just like a stick on a cart, and the cart moves and tries to balance the stick. And so you get a high reward if the stick is perfectly straight and less if it falls over. So basically we have in our environment space and our actions, our observation space and action space. Observation is basically this thing, it's called a box, but it's also basically a 4-dimensional vector. And then our action space is basically a discrete 2D binary vector. Yeah. Wait, actually, it might be a 1 value with 2 options. So basically go left or right, I think. Yeah. Okay. So we're gonna just do a random baseline. So we just do for 100 episodes. So within these, or 1,000 episodes, we'll have our total reward and count that over time. So we get our first state by resetting the environment, and then while it's not done, we just step through the environment. This env.actionspace.sample just samples a random action, and then we pass that into our environment right here, and so we get a state, reward, done, and info. State is the current observation state, and it's according to this right here, the observation space. And then we have reward, done, and info. Reward, of course, is explanatory, and then done tells us when it's done, and info is just like debugging info. You'll have that for all environments, basically. So this is standardized across all environments. And then we just sum up the reward and then increment the step. And then we'll just find the mean and standard deviation afterwards. So when we run this, we get this. So this is the average. These are the average returns. So this basically the sum of rewards over time. And then this is the mean number of steps it takes before the environment says it's done. Okay, so now we'll just create a simple policy with PyTorch. So we just make a linear feed-forward connection, and then our softmax determines what action to take. And then we just do that. Oh, maybe I have to uncomment this. Okay. Okay, so initialized. And then we create our optimizer. We'll just use stochastic rate and descent. And we pass in our policy parameters, and we set the learning rate to extremely low. I just played around with this, and this was the learning rate I needed to set to. Oh, but it's actually 2 to the power of -13. So it's not, I kind of defined it pretty whack here. But now we set our gamma. This is like the term that multiplies the rewards over time. So this gets smaller and smaller as you increase the time steps, and we have our episodes and the same stuff as before. We have our memory to store all the states, rewards, and actions. And then we have our episode rewards. Okay, so now basically we have to do a couple of things. First, we sample actions probabilities from our model, our policy thing here. And then using those, we basically put it into a categorical distribution, because now we have probabilities, and then we basically sample an action according to that distribution. And then using that action, we take one step in the environment, record all of the information there, and then pass it into the memory, etc. And so that's the first step. So we'll do this for a single episode. And then the second part is now we're training the policy. So basically we enumerate over the memory. So the memory contains one trajectory, essentially. So the memory at one time step is this. It's a tuple of 4 things. And so to train our policy, basically we first make sure it starts from 0 with 0 grad, and then we take our action probabilities with our policy, and then we calculate the distribution from our action probabilities, and then we want to calculate, this is the return, so G is the return, and so basically here we are calculating the return and then multiplying it by gamma. So this is dependent on how far into the trajectory you are. And then this is our loss, basically, and then we do one gradient step based on this. Okay, and then afterwards we just save the information. And so we can run this. And right now it's pretty slow because we didn't vectorize over the time steps, right? And we don't have any number of batches as well. So you could improve this by generating more data first and then doing batch gradient descent afterwards. So here, seems like it's going to take around 12 minutes to finish. And yeah, so that's basically it. So this will take a while to train, but I have another thing here. This is the reinforce algorithm. It's like the first policy gradient algorithm, and it also has a baseline function. This thing I didn't mention before, but basically a baseline function, it subtracts the expected reward minus some term. So basically you normalize how much expected reward you would achieve in the future. Because, for example, if you're seeing expected reward of always positive numbers, like that doesn't seem any new to the agent, so the agent might think it's always doing good. So instead we subtract it by some amount, so it's close to 0, and so now the agent might not be so optimistic about what it's currently doing. And so therefore it would try to learn things better. And we do this by learning a value function in combination. So this is basically also trained on our data, and we try to approximate what is the expected future return. And so when you plot the reward over the training steps, you can see that the policy improves, but it's very stochastic because we have a stochastic policy, and also this is a very old algorithm. It's not like the best one, so it should be like very unstable. Okay, so that's all I had for today. Any questions about the algorithm or anything else? Okay, so for future references, I really like these two references here. So if you really want to dive deep into reinforcement learning, this one is good. It's basically the go-to textbook for reinforcement learning. It's by Richard Sutton and Andrew Barto, and they're like basically the godfathers of reinforcement learning. If it's equivalent to like the deep godfathers of deep learning, like Jeff Hinton and like Yoshua Bengio, Yann LeCun, etc. And so spinning up in DeepRL is made by OpenAI, and they have great in-depth stuff. So they go over policy optimization like I did, and they also have the most recent state-of-the-art algorithms here that you can look into yourself if you want. And they also have code in this too. And recently they just switched over, like the whole of OpenAI switched over to PyTorch very recently. So now they have implementations of this in PyTorch as well. So yeah, that's all. So thank you for coming.